Now what we're going to look at next is how to determine both empirical and molecular formulas. So to start with this, we need to talk about a concept called percent composition. This is just the percentage by mass of each element in a compound. So let's take, for example, a 10-gram sample that contains 2.5 grams of hydrogen and 7.5 grams of carbon. We could ask the question, what percentage by mass of this compound is hydrogen versus how much of it is carbon? So the general equation for any percentage is just percent equals part over whole times 100%. And that's what turns into a percentage. So there's a percent sign on these. So what we do is the total compound has a mass of 10 grams. That's our whole. Then for the hydrogen, there are 2.5 grams of hydrogen. So 2.5 divided by 100. If you then multiply it by 100%, will give you that 25% of this compound is made of hydrogen. And then for carbon, you do the same calculation. You get 75% of this compound is made of carbon. The reason this is helpful is that a lot of times when we find the identity of a molecule is we will take the molecule, we'll then put it into an instrument that's going to heat it up a whole lot or some other way add energy into it. And when it does that, the molecule is going to break apart into its separate atoms. Then we can do some, it's not really voodoo magic, it's chemistry, but we do some work to do something called mass spectrometry, where we will somehow charge those molecules because it's much easier to work with things that are electrically charged. And then we will somehow accelerate them so that they go down, like, for example, maybe a big long tube. Like you run a race with the molecules, and the light molecules go faster than the heavy molecules. That's a time-of-flight mass spectrometry. You don't have to know that name. There are other techniques we can use. So basically, there's a whole bunch of different forms of mass spectrometry. But in some way, we make the atoms go, and we can tell the difference between them based on how fast they go or some other property that we use. And so we figure out, of these molecules, how many of them are hydrogen versus how many of them are carbon or oxygen or fluorine or whatever it is in our molecule. And we can use that to figure out the component pieces that made up the molecule that we broke apart. And so from that, we can find a percent composition, and we can use that to help figure out what the molecule's made of when we don't know what it starts with. That's a big change when you think about what we're doing in class versus what you might be doing in other situations, like in a job or you're applying chemistry somewhere. Most of the problems we solve, I start by telling you, hey, you have this thing. There'll be a lot of circumstances where you're using chemistry where you're like, I'm not sure what I have. In reality, someone might have hired you to figure out what they had. They're like, we don't know what this is, but they probably have some guess, right? Like, it's not just randomly like, here's a substance. It could be anything on Earth. Go. There are things related to that where that is what you're doing, but most of the times it's not the case, right? Most times it's, I think I have X, but it could be Y, or it could be a related molecule. Can you tell me what it is? Well, Dr. Leslie can, because he's got instrumentation to do that with, and that's why one of the main reasons we get jobs as chemists. A lot of chemistry is, I think I got something. Can you confirm that I have this? Or, I have something. Can you tell me how much of it there is? Really, that relates to a lot of our job, in many cases as chemists. Not all of it. There's plenty of people that don't do that at all, that do other things. But just a very common category of, what do you do with chemistry? I tell you what you have, or confirm it, and I tell you how much of it you have. That does a lot of stuff, and there's lots of cases where we worry about that. Like, hey, I want to know, do I have a pollutant in my water? If so, how much is it? Is it enough that the EPA would care? Is it enough that my town should spend some extra money to filter this thing, or is it perfectly fine and safe for everyone to drink already? So, how do we take information to find out what it is we have? Well, that's what we're going to look at here. Determining the percent composition from molecular or empirical formulas. Okay, this is the backwards version. I'll show you how to do it from data first, after this. But so this is the other way of doing it. This is what the percent composition would be from the formula, and then we'll go the other way. I'll show you how to find the percent composition and then determine the formula. This version's easier, but still good to know. Teaches the base idea. Let's take the molecule NH3. I want to know what percentage of NH3 should be nitrogen and what percentage should be hydrogen, which means I should get those same results when I'm testing them if I do have what I think I do. So I'm testing a sample that I think is ammonia. What should the answer come out as? Well, what you do is we have an equation here. So again, part over whole. So in this case, we're looking at the molecule overall. And so this is specifically for percent composition of a molecule. So we'll take percentage of whatever atom it is we're interested in finding the answer to. We'll get the mass of that atom in the molecule divided by the mass of the molecule. and we'll multiply it times 100%. And you'll notice this is just our percentage formula, part of our whole. We're just defining what the part and whole are. So in the case of nitrogen, there's only one nitrogen atom. It has a molar mass of 14.01 AMUs, or 14.01 grams per mole. And the total molar mass of NH3 is 17.03. So if I divide those two together and multiply 100, I get that this should be 82.27% nitrogen by mass. So if I do an analysis of a substance that I think is NH3, that should be the answer I get. We then check for the hydrogen. One hydrogen has a molar mass of 1.008 AMUs, or grams per mole, but there are 3 of them, so I have to multiply it by 3. So we have 3 times that divided by 17.03. We work that out. We get 17.76% hydrogen. And if you have NH3, no other atom should come out. So you should get these 2 percentages in any test where you thought you had NH3. So that's the idea. This is what we would expect to see if we did that. Now, let's look at this another way. What if I don't know the formula and I'm trying to take some data to figure it out? So how do we do that? So first I want to remind you that an empirical formula are the simplest whole number ratios of atoms or elements in a compound. This is important. The technique, the way I'm going to talk about this way to use data is going to be for solving for empirical formulas, not necessarily molecular formulas. There's some other information we would have to get to solve for molecular formula, which I'll show you how to do. But so I'm showing you how to find the ratio. But NH3 versus N2H6, if that thing would both give you the same readout I just gave you. Nope, you're not going to find N2H6. The electrons aren't going to work out for that molecule. But if it did exist, it would look the exact same as NH3. So I'm looking at what the ratios are of this. So an elemental analysis is going to tell you what the ratio of the different atoms are. And so we're going to look at how do we determine from some data about, hey, what masses came out of this particular substance, what was the empirical formula for that substance. And then we'll look at how to get a molecular formula afterwards. Like there's some extra information you'd have to be given or have another experiment to do to find out. So note, I promise we'll solve an example with this, and that's what we'll do. There's a bunch of words in the slide, but we'll go through all of it. So we're going to start with an example, which is, let's say I did an analysis, I ran through a GC mass spec, and I got, it's a type of mass spectrometry, don't worry about the specific version, but it's that, let's say it was 25.9% nitrogen and 74.1% oxygen. And someone asked me, Dr. Leslie, what is the empirical formula of this thing? Let me compare it to what I was thinking I had. Let's see if they're the same thing. So there are 4 steps you're going to go through. The first is going to be, if you're given a percentage, convert this to grams. If you're already in grams, skip this part. What you're doing here is you're acknowledging that this percentage ratio could be for any starting mass. But to make your life simple, treat it like you had a 100 gram sample. So 25.9% of 100 grams is just 25.9 grams. So we're going to work with 25.9 grams of nitrogen and 74.1 grams of oxygen. You could do a different starting number, but it would make your problem harder, that's all. You could say 50 grams, find out what 25.9% of 50 is, and 74.1% of 50 is. You would get the same final answer, but it's extra work. So just set the percentage to grams and you're good to go. Step 2 is we have to convert these to moles. We're interested in how many atoms there are. That doesn't tell us based on the mass, so we need to do that conversion. So I'm going to take 25.9 grams of nitrogen first, and we're going to convert that using the fact that 14.01 grams of nitrogen contains 1 mole of nitrogen. And so I'm going to get a number for this, and let's see what we got. We have 1.85 moles nitrogen. I'll do the same thing for oxygen. 74.1 grams of oxygen. Each oxygen mole is going to contain 16 grams of oxygen per 1 mole of oxygen. And so we do 74.1 divided by 16. And this is going to give me 4.63 moles of oxygen. Now the issue here is you would not write that you have N 1.85 O 4.63, right? That doesn't look like a formula that we would use. It is true that the ratio is 1.85 to 4.63, but we want these in a whole number ratio so they work like molecules we're used to using, so that it actually matches up with how many atoms could be a part of one molecule. So what I'm going to do is I'm going to divide every answer I got in this question by the smallest number I got. Effectively, I'm setting one of the atoms to 1. Note, there will be some changes afterwards. Sometimes you won't always have, sometimes all of them are are numbers other than 1, but this is a good starting point. So I do this, I'll get 1 nitrogen, and then 4.63 divided by 1.85 is 2.5 oxygens. Now again, that doesn't match up well yet. We're not done yet, because that would be NO2.5. And that again doesn't look like a molecule we would work with, right? We expect whole numbers. So the final step is you will, and because it's a ratio, any changes you make, you have to do everything. I can't just change the oxygen, so don't just round the oxygen to 2 or 3 here. That will not give you the right answer. What you do is you multiply by the smallest whole number that will get rid of all the decimals. So for example, this one ends in 0.5. If I multiply it by 2, 2.5 times 2 goes to 5. So I'm going to multiply both of these by 2. That will give me 2 nitrogens and 5 oxygens, which is now an acceptable ratio, N2O5. And so that's our last step. We've got to multiply by whatever number would get rid of the decimals. Now, a reasonable follow-up might be, Dr. Leslie, how'd you pick 2? That felt kind of random. And if it didn't, good for you. If you're really great at ratios and fractions already and you're real comfortable, you can move on from here. But if you would like to know how I did that, it's based on what the decimal ended with. It's related to the fraction specifically they're compared to. And we'll go over all the ones you're going to use a lot in this class. So for example, 0.5, we multiply by 2 because that's the 0.5 represents the fraction 1/2. On the other hand, the fractions 1/3 and 2/3 represented by 0.33 and 0.66. So you have something really close to these, you'd multiply it by 3 because that would get rid of the fraction. Well, let's say you had something close to 1/4 or 3/4. That would be 0.25 or 0.75. I would multiply anything really close to those by 4. You don't have to put 0.5 because that's related to the fraction 1/2 because 2/4 simplifies to 1/2. So I wouldn't have to worry about 0.5 with this one. I can just multiply that by 2. Then let's say I had like 1/5 or 2/5. If I had, I'll do it over here. There's more room. 0.2, 0.4, 0.6, 0.8. For these, I'm going to multiply by 5. Now, something else to note is we are working with real numbers. What this means is sometimes you'll get decimals that aren't perfectly round, but are really close to something, and then it's reasonable just to round it up to the nearest number. So for example, if I got 3.99, I would just round that to 4. In general, anything above 0.9 or below 0.1, you can just round those numbers to the nearest whole number. If it's further away, though, then you need to multiply by either one of these numbers like 2, 3, 4, or 5. Technically, you could have some other ratio for a very complicated molecule that would require you to do something bigger, but it is reasonably uncommon and not for any of the things we're going to work on in this class. So if you get something really close, choose that. So for example, if I did a calculation, I'm writing in the upper right corner now, and I got, let's say, 4.32 grams of nitrogen. Well, you can multiply that times 3. It's 10, and when you do that, 4.32 times 3 will give you 12.96 grams nitrogen. At that point, or sorry, these will be moles, not grams. Moles. And at that point, you're so close that you're good with working with that number that you can round that. That can be 13. So it's okay to do some rounding. Just wait till you get within above 0.9 or below 0.1 is a good ballpark estimate here. Long term, if you're in sciences, you'll have times where you wouldn't round there. You've got other external knowledge you can use to help apply to these situations. That's the idea, is they're always contextual to what you're working with. But for this class, this will be a good enough approximation to get through any of our questions. Here's a second example given from your text. Let's take a compound that contains 5.31 grams of chlorine and 8.40 grams of oxygen. What you'll notice with this is we are already in grams, so you don't have to worry about dividing into moles. So you can just take this and divide both by, okay. So you've got to divide this into moles. That's right. So 5.31, I put my number in the wrong place. So you have 35.45 grams of chlorine per 1 mole. 5.31 divided by 35.45 will give you 0.150 moles of chlorine. And then your 8.40 grams of oxygen, you've got 16 grams of oxygen is 1 mole. So 8.4 divided by 16 is going to give you 0.525 moles oxygen. And note, your textbook just writes a little bit differently. They go ahead and they put it in this form over here, and then they do the division. So this division here in this next step is just the same thing we're doing. If you like it written better like this, you can, or you can come up here and divide both these by 0.150. And when you do that, you'll get 3.5 oxygens, 1 chlorine. And from there, we've got to find the decimal to multiply to get rid of those decimals. And so in this case, again, 0.5 is the ending. If I multiply that by 2, it'll become 7, and the chlorine will become 2. So this molecule would be Cl2O7. So this is how you solve for empirical formulas. I will note you can have 3 or 4, you can have as many atoms as you want. Realistically, you're not going to go much above 4, and usually 2 or 3, just because this gets more complicated as you get a whole bunch of them. Same rules still apply. Divide by the smallest number, multiply by something that gets rid of all of the decimals. And I didn't mention all of them. You might get something where you've got to multiply by more than one number. So you multiply by 2 first, then 3 or something. So you've got to get rid of multiple decimals. That's okay when you do that. Now, let's look at another practice problem. And for this one, I suggest pause me and give this a try, and then see if my solution matches up with yours. I gave it a second for you to find time to find the pause button. Hopefully you have done that. Or if you got stuck, that's okay, and came back to low watch. So let's do this now with 3 atoms. So first I'm going to treat the percentages as just grams. So I've got 60.0 grams of carbon, and I want to convert that to moles. Its molar mass is 12.01 grams of carbon, is 1 mole of carbon. It's going to be about 5. 60 divided by 12.01 will give me 5.00 moles carbon. Then we have 4.5 grams of oxygen. Hydrogen. And it's got a molar mass of, I'm just going to go with 1.01 grams of hydrogen. You can also use 1.008. They're both fine. I find going to 2 significant figures in your 2 decimals in your molar mass is often plenty. 4.5 divided by 1.01. This will be 4.46 moles hydrogen. We then have oxygen, which is 35.5 grams of oxygen. Molar mass of 16.00 grams of oxygen per 1 mole of oxygen. 35.5 divided by 16 is 2.22 moles oxygen. So now I'm going to divide all 3 of these by 2.2 moles. And one of your answers is always going to be 1, and sometimes even it could be 2 of them even, but always at least 1. So this gives us 1 oxygen. We have 4.46 divided by 2.22. That'll be 2.01 hydrogens. Our carbon is 5 divided by 2.22, and that will be 2.25 carbons. Now, you'll notice that I've got 2 different decimals, but my 0.01 for hydrogen is effectively just 2. It's so close that I'm not going to worry about it. But my 0.25 carbons is not close. So I'm going to need to multiply all of these by 4. When I do that, I'm going to get 4, 8, 9 carbons. I'll get 8.04 hydrogens and 4 oxygens. And again, I kept the decimal for now, but I can see this is still good enough to round. I'm good with that just being 8 hydrogens. And so we have C9H8O4. This is the empirical formula for a molecule that has these 3 percentages for its mass. So this is how you solve a problem that had 3 compound elements. Otherwise, solved the same way, just you have to do all the steps in extra time for the 3rd element. That was all. Hopefully you notice this isn't too bad, and the pattern is very systematic, which helps. So even if there are a lot of steps, they always go in this same order, which can make problems easier to do. One final note I want to make with these, if you follow through all these steps, you shouldn't have this issue, but sometimes you might multiply by bigger numbers than you needed to. So for example, let's say instead you'd multiplied by 8, and you ended up with C18H16O8. If you have a case where all the numbers can be divided by something, you should do that to make them smaller. So in this case, I could divide all of these by 2, which would give me C9H8O4, which would be the correct answer in this case. So do make sure to check that. Most commonly, it's if you need to divide by 2. But just if your numbers end up really big, you can see is there something I can divide them by. To help simplify it, This is just like in any other problem where you want to solve the empirical formula from the molecular formula. You're looking for a lowest common multiple. If the lowest common multiple is 1, you're done if that's all it can be divided by. Now, everything I did up to that point was just empirical formulas. And I know there's a bunch of words in this slide, but we'll be okay. It's not too bad. So a molecular formula is specifically exactly how many atoms there are. And that sometimes is the same as the empirical formula, but not always. So you need extra information to solve these problems. So everything I've shown you so far, none of those problems gave enough information to solve for a molecular formula. So if you're going to solve for a molecular formula, I need to somehow give you information with the molar mass of the molecule. Because what you need to know is what this value n is, which is the ratio between the molar mass of the molecular formula and the empirical formula. So the example I give down here is if the true molecule was C3H6, but you calculated an empirical formula of CH2, you would need to somehow know that you need to have 3 of these CH2 units to be able to get up to the true formula. So CH2 is still a good answer for an empirical formula. So somehow I have to give you the information to be able to solve this ratio. And for the purpose of this class, the only way I'm going to do this is I'm going to give you the molar mass of the compound. So I'll give you all the information you just saw, and then I'll also give you a molar mass, which means you'll have a step at the very end where you go and figure out, does the empirical formula mass match this, or is it smaller? And if it's smaller, how much smaller so you know what to multiply by? So let's take a look at an example of this. I think that's easier than just trying to read through a bunch of these words. But the idea is molecular formulas sometimes have multiple units of your empirical formula combined together, and you need information to be able to do that. So this is an example from your text. So the text shows that, let's say you calculate an empirical formula of CH2O. That has a formula mass of 30 AMUs. But you're told the molecular mass is 180. What you do is you take your molar mass and divide by your empirical formula mass. So in this case, you take 180, divide it by 30, and we do that, you get 6. This number should always be a whole number. So if you get something with real numbers that you're using, and it's like 5.95, round that to 6. Or 4.03, round that to 4. So in this case, it was 6. So you have to multiply this CH2O times 6 for each atom. Remember, there's an understood 1 for each of those. So you multiply by 6 by all 3 of these numbers, and that gives you C6H12O6. So this is how I would do it if I were to give you an empirical formula and I wanted you to find the molecular formula from that empirical formula. I would have to tell you the molecular mass. You can't get that on your own. You need that information from somewhere. Now, here's an example of how it could be done in a problem where you have to do both steps. First, find the empirical formula, then find the molecular formula. So this is the more involved version. So we'll start, just do all the empirical formula steps first. Don't worry about the molar mass till the very end. So right now I'm just focused on these percentages. This number down here is for later, once we find the empirical formula. So we've got 39.97 grams of carbon. We have 12.01 grams of carbon per 1 mole. So 39.97 divided by 12.01. That'll give 3.33 moles carbon. We then have 13.41 grams hydrogen. 1.01 grams hydrogen per 1 mole hydrogen. Won't change it a lot, but will a little bit. So let's calculate that. That'll be 13.28 moles hydrogen. And then finally, 46.62 grams nitrogen. You've got 14.01 grams nitrogen per 1 mole nitrogen. 46.62 divided by 14.01. That's going to give 3.33 moles nitrogen. So now I divide all 3 by the smallest number, which in this case is 3.33 moles. 3.33, 3.33. And when I do that, 2 of mine are going to turn out to be 1, because they have the same value in front. So we've got 1 nitrogen, 1 carbon, and then 13.28 divided by 3.33. We've got 3.99 hydrogen, which is close enough, we'll just call it 4 hydrogen. So our empirical formula is CH4N. But this is not necessarily our molecular formula. We have to determine that by finding the molar mass of our empirical formula. So its molar mass, so the molar mass, or formula mass, I'll use that term better because we don't know if this is the one for the molecule yet. The formula mass for this compound, I look up. Nitrogen is 14.01 grams per mole, carbon is 12.01 grams per mole, and hydrogen is 1.01 grams per mole, but I have 4 of them. So it's 4.04 grams per mole for it. I then add all those numbers together, which will give me, if I put things in my calculator right, a molar mass of 30.06 grams per mole. You'll notice this number and this number are not equal. So this is not the molecular formula, even though it's the empirical formula. I need to solve for what is the ratio between them. So I take 60.10 grams per mole, divide it by 30.06, and I can see from this is going to end up at 2. So, I mean, technically it'll be a tiny bit off 2 because these are numbers that have some rounding, but you'll round it to 2 after you do that, but I'll go ahead and just check. So yeah, I got 1.999, which is 2. So I need to double every component in the formula mass to get the molecule. That means we have C2H8N2. And this would be the molecular formula. So this is our molecular formula. Whereas this up here, this one, was our empirical formula. The empirical formula was the ratio of the atoms. The molecular formula was exactly how many atoms are in one of these molecules. Do note that sometimes the empirical formula is all you can find. So it's not always going to be necessary to find a molecular formula. You may not have the information necessary to do so. The molecular formula requires more than just the percentages or the number of grams of each substance. You need some other experiment or piece of information to know its molar mass, to be able to figure that out. So if you don't have that molar mass information in some way, you just have to stop at the empirical formula, which will be the case in many examples, and that's perfectly fine. And that ends our discussion of both empirical formulas and molecular formulas. Note that for molecular formulas, many times it's you just do the empirical formula stuff, plus do one more step to convert it. Although, going back a slide, you'll sometimes have problems like this, where it is a very quick problem, where it is, no, we're already giving you the empirical formula, just find this ratio. Be comfortable with both. So it's okay if it's the short version or this longer version here. Be able to solve problems of both styles, and you should be good to go for this section.